Welcome to Oddly Real. I'm Nem Stefanovic. What if there's something that is everywhere, permeating our entire universe, and yet it's not necessarily anywhere specific? Additionally, what if this thing doesn't exist in one particular form, but can be a number of different forms and even readily changes from one form into another? What if the very nature of our universe is governed by a strict law that ensures this quantity remains preserved, never to be created or destroyed, but maintained in its quantity for eternity? I'm of course talking about the energy in our universe. Energy is both an abstraction, something that we can calculate as a number, but it's also something that is real, with physical implications for how nature works. Even the very existence of something, like physical matter, is attributable to a form of energy. Moreover, the law of conservation of energy is not only a rule that applies to particular situations in physics, but it applies universally across all sciences and all of nature in the entire universe. It's truly one of the foundations of our reality. In this episode, we'll discuss what energy is and provide real-world examples to better understand it. What exactly is energy? One common definition of energy is the capacity to do work. For example, you would do work or expend energy to push a heavy object across the floor. Alternatively, if an object is in motion, traveling at a certain speed, we'd say that that object possesses kinetic energy. There is also energy in how an object is positioned relative to another in space, which we would call potential energy. For example, if we lift a massive object off of the ground, we would have to do work or use energy to counteract the force of gravity. That object is now positioned away from the Earth in such a way that it possesses gravitational potential energy. Notice it's not moving, so there's no kinetic energy. Yet, if we now let go of the object, it's clear that there's energy there, since the object will begin to move by falling down, and you'll see it take on kinetic energy. Notice that in these described situations, there are very real physical effects that are associated with energy. However, the actual quantity of energy itself is really an abstraction. It's a number that we calculate. For example, we calculate the energy expended to push a heavy object across the floor by knowing the force that we applied over the distance that the object moved. We can also calculate the energy of an object in motion by knowing the object's mass and its velocity to get a value for its kinetic energy. Furthermore, we can calculate the gravitational potential energy of an object that we lift up off of the ground from its mass and height. Notice that these are different situations, yet in each case, there's a calculable numerical value that represents an energy. In fact, there are many more situations where energy can take on a variety of different forms. If you take a metallic spring and stretch it out, you'll notice that the spring will return to its original shape once you release it. When the spring is stretched out, it holds elastic potential energy in the matter in the spring, which is being distended or stretched. Electrical energy comes in the arrangement of charges, either attracted or repelled, or the motion of those charges. Chemical energy, which is inherently electrical in nature, involves making and breaking chemical bonds to store or release energy. Radiant energy involves the transmission of electromagnetic radiation, such as radio waves, light, X-rays, and any other wave in the EM spectrum. Nuclear energy is derived from the arrangement of particles inside the atomic nucleus. There is even mass energy, which is the energy associated with the sheer existence of a material object. This energy can be spectacularly demonstrated with an annihilation reaction, such as between an electron and a positron. This results in the production of radiant energy, like gamma rays, according to E equals mc squared. It is amazing that in all of these different physical situations, we are able to compute a value of a common quantity, energy. Energy is truly pervasive across nature. It turns out that not only can energy exist in many different forms, but energy is able to readily convert between these forms. It is experimentally verifiable that when energy converts from one form into another, the amount of energy is preserved when transferred over. There is a greater law that governs energy in our universe called the law of conservation of energy. Specifically, energy can neither be created nor destroyed, only converted from one form to another. This is also called the first law of thermodynamics. If we assume there is nothing beyond our universe, then one implication of this law is that the total energy of the universe is constant. Let's look at an example to help illustrate some fundamental properties of energy. Let's look at a pendulum, which is just a mass attached to a string. To keep things simple, we'll assume it's idealized, so we can disregard things like friction. If the pendulum starts with a mass at its lowest position without any motion, nothing happens and it stays in that position. However, we can add energy to the system by lifting the mass up to a new position. This spatial repositioning of the mass against the force of gravity means the system now has potential energy, or energy associated with a position. Where did that energy come from? Our body did work on the mass. Our muscles contracted to produce a force in opposition to gravity that was applied over a distance up to the new height of the mass. In fact, the muscles expended energy which originated from the food that we ate. We know there is energy in the new position of the mass since when we let go, all of a sudden, the mass is set in motion to begin swinging. Notice that when we talk about potential energy, what we really mean is the energy at a position relative to another position. In this case, the energy of the mass, when lifted, is the energy relative to the lowest position in the pendulum. Since this energy at the bottom of the pendulum is really just a reference point, we can just say that represents zero energy for our example. Notice that as the pendulum swings, it will move from one height on one side to its low point and back to the same height on the other side. That makes sense since we assumed the system was ideal without friction, so there should be no energy losses as it moves. If there was a potential energy associated with the pendulum mass on one side, we'd expect to see the mass reach the same height, which represents the same energy when swinging to the other side. But there's something strange here. If the mass swings through the bottom position of the pendulum, doesn't that mean that the energy is zero there, since the height is zero? And if so, where did the energy go? It's true that the potential energy, which is the energy of position or height in this case, is indeed zero at the bottom position. However, recall that the law of conservation of energy means that energy is never lost. It can only be transformed into another kind of energy. In this example, the energy of the mass at the bottom of the pendulum position is now entirely converted into the form of kinetic energy, or the energy of motion. The kinetic energy here is exactly equal to the energy that we put into the system in the form of potential energy. Here, the mass is moving at its fastest speed, which is also why the pendulum continues through this point, steadily slowing down until it reaches its peak, where all of the kinetic energy has been fully reconverted into potential energy. This process continues indefinitely under idealized conditions, converting between potential and kinetic energy. This example illustrates the two fundamental forms of energy, kinetic and potential. And it also demonstrates how energy is transformed between the two. Energy can be transferred between two objects in two ways. First, it can be transferred in the form of work. This is what is meant by applying a force over a distance. This is also the concept behind useful energy, or energy that we can use as human beings to accomplish purposeful tasks. Alternatively, the second kind of energy transfer involves a workless transfer of energy, or energy in the form of heat. Based on the first law of thermodynamics, which states that energy is neither created nor destroyed, It means that energy is equal to work plus heat. In fact, we can generalize this concept even further by defining the internal energy of a system. Internal energy, U, is equal to work, W, plus heat, Q, where the internal energy is associated with atomic structures and motions. For example, consider a glass of ice compared to a glass of water. If we only considered the potential energies of the glasses and the kinetic energies of the glasses, we'd find that in both cases the potential and kinetic energies are zero. This is because the glasses are both at the same height relative to the surface, and the glasses are also not in motion. However, there's a clear difference between the contents of each glass. One has ice and the other has liquid water. At the atomic level, the atoms in the ice have less energy. They are locked into a crystal lattice with minimum motion. However, the molecules in the water have more energy of motion as they slip and rotate and move around other molecules. The internal energy of the liquid water is larger than the internal energy of the ice. If we applied heat to the glass containing ice, we would be adding energy to the system to turn the ice into water. Yet, the kinetic and potential energy of the glass would still be zero. Internal energy is what lets us account for these kinds of energy differences. Another interesting implication of the law of conservation of energy is that both work and heat are completely equivalent to each other. If you have a system like a pot of boiling water, there's no way to tell how that water was made to boil. It could have been boiled by the direct application of heat to increase the temperature of the water. However, it is also possible that the motion of the water molecules could have been increased by mechanically stirring them, which also results in the increase of water temperature. Ultimately, there is no distinction to say which approach was used. Work and heat are both forms of energy and completely equivalent. We mentioned that energy in the form of work is applied to a system when a force is applied over a distance. However, this too can be generalized as a thermodynamic force applied over a thermodynamic displacement. This is also work to supply energy that results in a configuration change to the system. For example, we can apply a pressure to something that produces a change in volume, which results in mechanical work. In another example, a chemical potential of a substance, which is its tendency to absorb or release energy in a reaction, times a change in the quantity of the substance results in chemical work. Interestingly, there's also a generalized form of representation for the energy of heat. It turns out that heat energy is equal to the temperature of a substance times its change in entropy. Recall that entropy is a measure of possible arrangements of the atomic structure of the substance, or roughly speaking, its level of disorder. Entropy is the link between heat and temperature. Heat is the transfer of energy of a system due to thermal interactions with a transfer of entropy. I hope you enjoyed this episode, and remember, oddly real, really interesting.